So good morning, everyone. Do you hear me now? Okay. So good morning, everyone. First of all, let me thank the organizer for giving me an opportunity for this talk. It's really a pleasure to be here, this very nice place, and to talk to you about my work. So today I will talk about non-LTE, like non-LTE modeling or non-LTE calculations for a large cyclic molecular species. Currently, I am employed in the ATOMKI Institute of the Hungarian Research Network, but this work was started in REN in the group of when I was a postdoc in the group of François Lick. So it was done within the Colloque ERC project. And so it's a bit hard to give give the details of the motivation about this work after the very nice and excellent talk of Jérôme Louraud, who did a very nice introduction of the field of the importance of collisional excitation studies and molecular collisions in general. But I would like to briefly summarize some details about like why we are motivated to do this work. So collisional excitation studies are important to understand the physicochemical processes of interstellar molecular clouds. So in interstellar molecular clouds, which are an active star-forming regions of the ISM, they are consisting of mostly gas, and some part is dust. And the usual density is ranging between 10 and 10 to the minus 8 particles per cubic centimeters. And the temperature is also ranging in a very broad range. It can range from a few Kelvin up to thousands of Kelvin in some parts of the clouds. And there is a specific attention on cold molecular clouds, like, for example, the Taurus molecular clouds, the TMC1, which is very often targeted now. For example, the group of Pepe Sarnicero, who is here at the moment. So in these clouds, the temperature is usually very low, so below 10 Kelvin, and the density is usually ranging in between 10 to power 4 to 10 to power 6 particles per cubic centimeters, which is usually the typical regime for non-LTE excitation. So these cold molecular clouds are extremely rich in chemistry. So there are a lot of long cyanopolyene chains recently observed, HCN type of chains with carbon atoms which ranging from 3 to 11 even. And there is a lot of complex organic molecules and polycyclic aromatic hydrocarbons, which was recently observed, including, for example, cyclic cyclopentadiene, or, for example, benzonitrile, which was the first of this type of molecule detected in the TMC1 molecular cloud. And also there is cyanocyclopentadiene and indene, so double ring structure and so on. So there is a special attention on this. So as Jérôme already introduced, so what's the importance of collisional excitation for studies in non-local thermodynamic equilibrium environments? So in these environments, the radiative and collisional processes are compete with each other to populate the molecular levels. So simply there is not enough collisions between particles to make a local thermodynamic equilibrium condition. So that's why we need, except for the radiative coefficients, so the Einstein coefficients for emission and absorption, we also need collisional excitation and the excitation rate coefficients for the different particles. In collisions with the most abundant interstellar colliders, like it's dominantly it's molecular hydrogen, H2, and helium in the interstellar medium. And so this allows us to perform non-LTE radiative transfer modeling to interpret molecular observations, or the lines which are observed in these clouds, and derive the correct physical conditions and molecular abundances in these environments. So Jérôme also mentioned about this. So the current state of the art is we can say rather poor at the moment. So there is at more than 300, or even yesterday I think I saw in a talk that there is more than 330 molecules already detected in the interstellar medium, and only for about 70 of them there are collisional data available at the moment. And this is a recent paper which talks about the state of the art of the base call database, which is one of the most widely used databases with collisional excitation rate coefficients. And so for polyatomic symmetric top species and polyatomic symmetric asymmetric top species, the data are even more rare. Let's say, like usually we have enough data for diatomic, triatomic species, most of the linear species, but we still still have a lot of things to do for polyatomic species. And this is also the case in other databases like EMAA and Lambda, for example. So about large cyclic species, there are only a few studies. There was a few studies earlier. One of them was the benzene, which was studied in collisions with helium by a mixed quantum classical theory. And just after that, there was a study of benzonitrile, which was studied in collisions with helium by the coupled state method by the group of Jérôme Leroux, for example. And so we started to study the cyclopentadiene, C5H6, recently. This molecule was detected first time by Pepe Sernicharo's group in 2021 in TMC1, and rather recently it was detected again in other cold molecular clouds by the same group. So it's a closed shell asymmetric top molecule, which belongs to the C2V point group. So we calculated the collisional complex with helium as a first target, let's say. So we calculated in total more than 12,000 points to sample the potential energy surface with a rather high level of quantum chemical theory. And this is the graphical representation of the molecule and the coordinate system which we used for these calculations. We found that it has a rather shallow well, but the global minimum is located at rather large distances, so it forms a typical van der Waals complex. So it's a non-reactive complex with helium, as expected, and there is a lot of secondary minima along the potential energy surface. So here are some plots, for example, some contour plots about the three-dimensional potential energy surface which we calculated. So at some fixed azimuthal angles, for example, this is at phi equals 90, where we see the global minimum of the potential here. This is the intermolecular distance here along the y-axis, and here is the spherical angle theta. And we can see that it's really highly anisotropic because, for example, at a specific distance like 6 Bohr or 6 atomic units, we can see at some orientation the global well of the potential, and just moving a little bit, rotating a little bit helium, the atom around the molecule, we can see highly repulsive potential. So just pay attention that the scale is not linear. So we have a repulsive region only with this color. So in this region, and here so we have an attractive region of the PES in this region where we have a negative potential, and all the other regions are highly repulsive usually. So, and here is another plot which shows the angular dependence or angular anisotropy of the PES at fixed intermolecular distances. So this is a very nice picture because it's really at this specific distance of 8 Bohr, for example, we can really map the position of the hydrogen atoms. So we will see, of course, in the vicinity of the hydrogen atoms, when the helium is close to them, then it sees a very repulsive potential. And if it is between these spaces, so for example, in these regions which are shown in purple, in these regions, the helium can be trapped in an attractive potential. So once this potential energy surface was calculated, we proceeded to calculations of rotational excitation and excitation cross sections, both for ortho different nuclear spin species of cyclopentadiene. We used the full quantum and numerically exact coupled channel quantum scattering method, and also we use some part of the calculations, the approximate CS method. So we calculated the cross sections up to 500 wave numbers, and then this allowed us to derive based on this Maxwell-Boltzmann averaging the thermal rate coefficients up to 50 Kelvin. So this means that by the numerically exact CC method, we calculated the lowest 55 rotational states and all the transitions between them. So it means that below 25 wave numbers, so rotational energies, all rotational energies which or levels which has less than 25 wave number energy is calculated with the full CC method, and then we extended the calculations also to by using the CS theory for higher levels. So everything is below which is between 25, all states which are between 25 wave numbers and 100 wave numbers are calculated then with the approximate CS theory. And this is simply because numerically it was impossible to use the full close coupling method for these levels, because the computational time and the number of coupled channels are simply exploded. This is what Jerome explained also, like if we have many more states, then the number of coupled equations increasing very heavily, and that makes the calculations impossible. This is just to illustrate also the complexity of the rotational structure of this molecule. So this molecule has a rather low dipole moment, so below 1, and also very low rotational constants. You can see that it's around 0.2 wave. Some of them are around 0.2 wave numbers. It means that even on this plot, as you can see, below 9 wave numbers internal energy, we have like more than 40 rotational states if we count both nuclear spin symmetries. So there is a lot of states. And so then this plot shows the cross sections which were calculated for the different the excitation channels towards the ground para C5H6 rotational states on the left, and ground state ortho rotational states on the right. And what is visible is that at very low energies, the cross sections are rather similar in terms of magnitude, but of course there is a lot of resonances. These are not the errors of the calculations, these oscillations, but these are due to heavy resonances in the cross sections. So these are the full close coupling calculations, so numerically exact dynamical calculations. So we see at low energies they are rather similar, but as the energy increases, they start to be separated to each other. There is a strong decrease with energy also, and there are some very favored channels, or let's say the excitation pathways, which are defined by the combination of the rotational quantum numbers. So we saw that in the case of the so-called KC conserving transitions, like for example on these plots, these two are KC conserving. So when we have J, K, and Ka and Kc quantum numbers, if the Kc quantum numbers doesn't change during the transitions, these transitions are the strongest. And if they change, even for example, the general delta J equals 0 or delta J equal 1 transitions, which are strong in the case of many other asymmetric top species, for example, according to spin selectivity rules. Here, it's not the case. Here, even these J conserving transitions are not as strong as the Kc conserving transitions. So this was rather surprising. So this can establish some propensity rules for also for higher levels. And also we compared the cross sections which were calculated with the CC and the CS theory. So we see that at low energies we have rather large differences between the two methods. So the solid line is the CC calculation, but as the energy increases, usually the differences starts to become more negligible. So it means that at higher energies it's quite safe to use the approximate CS method. But the differences can be up to a factor of 2. And here are some more direct comparison already in terms of rate coefficients, which we calculated. So here we provide a set of rate coefficients calculated from the CC method along the x-axis and from the CS method along the y-axis at 3 different temperatures, ranging from 5K to 30K. And we see that at 5K, which are the blue dots, there is a huge spread. So the approximate method cannot represent very correctly the magnitude of the rate coefficient. So there are up to a factor of 3 differences mostly. So these lines are the case for a factor of 3 differences. And as the temperature increases, we see that this deviations between the exact and the approximate scattering methods are less and less. So we can see this also by the main absolute error values. And just the last plot to show another important physical behavior of the rate coefficients. Here we compare the rate coefficients, or like a set of rate coefficients for the calculated at 10 and 30K, with those calculated for 5K, so very low temperatures. And we see that at the beginning, so at lower temperatures, the change is not too big. But once we increase the temperature from 5 to 30K, so these are the red dots, there could be in most of the cases up to a factor of 3 differences. So the rate coefficients very strongly depend on temperature, strongly decreasing. So with factors of 2, 3, even when the temperature change is not too much. So, and for the last, some take-home messages. So the number of large complex species observed in the ISM is intensively growing, and there is apart from the laboratory and spectroscopy measurements, we also need accurate theoretical data for the collisional excitation of these species in order to understand the observations better and to make a better interpretation. So we studied the first time a large collisional excitation of a large cyclic molecule from the exact close coupling method. And so we will provide soon a full set of rate coefficients along with some radiative transfer calculations where we will cover the range of temperatures up to 50K and the number of states up with those with J equals 25. So thank you for everyone who is collaborating in the project, in particular to the primary investigator François Lick, and also my other colleagues Sheikh Bob and Ben Khalifa, and also thank to Pepe Sernicharo and Marcelino Agundes for the ideas for these calculations. And thank you very much for your attention.